Hi, yeah, so I'm David Nolen. This talk is called Finding a Balance. I'm the lead developer of ClojureScript. ClojureScript is a dialect of Clojure that compiles to JavaScript. I think that open source programming language projects are an interesting thing to study. I think because they offer some insights into software practice that I think are unique. Of course, open source programming language projects share the same challenges you would encounter in any software endeavor, but I think there are things that are different and in fact could probably inform some of the things that we do in our products or our companies. So a little bit more about me. I'm a software engineer at Cognitect. Cognitect is a software consultancy. We believe that you can build simpler systems by embracing immutability and functional programming. We're the stewards of Clojure, ClojureScript, and a product called Datomic, which is an immutable relational database. So we use these three different technologies. Our clients use these, some combination of these three technologies. And we try to solve hard problems. You might not know, but Cognitect, you see this logo and you think, oh, Cognitect, big company. Cognitect is really small, right? There's about 50 people. I think there's only about 20 to 25 engineers. Often when we work with clients, it's only 2 engineers coming into some project trying to help them solve some hard problem. Clojure itself was created by one person, right? So a lot of the narrative that I want to talk about here is what happens when you want to do an open source programming language project and you really don't have Google resources or Apple resources, right? Google's doing Go, Apple's doing Swift. Even Python and Ruby have much larger communities. So a lot of our problem is how do we stay effective and sustainable given the fact that we have extremely limited resources? And I think this is actually not even that well understood within the Clojure community itself. And so we're going to talk about sort of the trade-offs and the sort of balance that we're trying to find. So I think that a scale is actually kind of a bad analogy for finding a balance. This is what you would think, you more on this side, less on this side. But actually software as a practice is actually very complicated. There's lots of factors, right? Programmers I think tend to overemphasize the importance of programming languages. Other people tend to overemphasize process or whatever. The truth is that it's a very complex interaction between these different choices that you'd make. So I'd like to pick a different analogy. For people who know my unlearned personality on Twitter, I go by Swan Odette. People know I'm a big fan of Go. If I'd shown this image a couple years ago, most of you would be scratching your heads. You wouldn't know what this is. But DeepMind, they did a very astounding AI event called the AlphaGo competition between AlphaGo and one of the strongest players in the world, Isidol, and they confidently defeated Isidol 4-1. Anyways, why do I think Go is a better analogy? So Go has been developed over thousands of years, originally from China. It's a territorial game. Black goes first, white goes second, and you're vying for territory. You're trying to control more of the board. You place stones. You're trying to make your borders encompass more area than your opponent. Over thousands of years, people have discovered that it's better to start in the corners. The corners, it's easy to grab an outpost, a little piece of territory. Often what happens, you play in a corner, your opponent tries to prevent you from doing that, and there's these things called joseki. And they're corner patterns where you're trying to control the corner, but of course you have to maintain some sort of balance. The opponent's going to get something. But the trick in Go is that you can't just treat each corner as individual things. The same way as in software, you can't pick any element of the thing that you're doing, your software practice, one thing isn't going to decide it. It's really the interaction between different parts of your software project. Team is one component, right? You need to make good decisions there. Process is another component, right? But team and process are going to interact in very deep ways, in fact, often unforeseen ways. And this is true in Go, right? What you choose in one corner has to relate to what you choose in a different corner. Architecture, and then programming language, right? And all these things have to be working in concert. You have to keep the whole thing in your head in order to hopefully get a successful result. As we know, even if you make good decisions in all these different parts of your software project, you may still fail. That happens all the time. And I think that, it's not like anything I'm going to say is going to solve any of these problems or any of these problems are going to get solved anytime soon. The importance here is that we should study the effects that our choices have, compare other choices that people have made, and see if we can at least, continue to improve our theory about how one can have success in a software project. I'm not going to talk about software practice at large, but again, I like the Go analogy because in Go, between two Go masters, it's very common that if somebody wins, you win by 1 point. There are 361 empty points on the board, yet somehow, between two masters, somebody wins by 1 point. In fact, in Japan, there's a famous saying where because black has the advantage, has the territorial advantage because they have the initiative, they used to say, if you were white and you lost by 1 point, that was your lifetime masterpiece. That's how finely balanced the game of Go is. And so I like that as an analogy. It shows how complicated the different elements interact if you're pointing towards success. But I'm not going to talk about the broader decisions that happen in software practice. I'm really interested in open source programming languages. So I want to focus on languages, and you can sort of apply this analogy in a recursive way. When you're setting out to do an open source programming language project, all these choices matter, right? What paradigm? So you could go functional, but that's not as popular as object-oriented. This is why it's unsurprising that most initiatives that lead to successful programming languages either are object-oriented or look very object-oriented. They look like things that people recognize. If you want a software project that's likely to fail, in terms of, when I say fail, I mean acquire a user base, an industrial user base, pick logic programming, right? There's just not enough knowledge in the mainstream to make that succeed, even though that's a very compelling paradigm. These days, programmers are very interested in, platforms, right? It used to be, as the previous speaker was saying, it used to be, you just got the manual and that's it. There's nothing else, right? But these days, most programmers are only interested in leveraging some existing platform, whether that's the JVM, whether it's iOS, Android, it doesn't matter. People don't care about raw technologies. They care about how can I succeed with the platform that we're targeting. Interop becomes important. Tooling is also important. People have very high expectations. If you look at software tools now versus the way it was before, I mean, it's night and day. I mean, if you're using Java and use IntelliJ and use the profiling tools, I mean, they're very powerful, sophisticated tools now for reasoning about software. If you're starting a new programming language, what are you giving your end users? As you look at some of the more cutting edge programming languages, and the tooling sucks, right? I mean, it takes a long time to get good tooling. So these are considerations. You can make choices that make tooling easier or harder. Performance is another dimension, and I got to keep going, but I think you get the analogy. So what does this mean for Clojure? So Clojure is, I think, a bit interesting in the sort of what's currently available. Clojure isn't new, right? Clojure's 10 years old. It's a dynamic Lisp that targets the JVM. Rich Hickey set out, he launched it. It was released 10, 11 years ago, even though he started in 2004. So that's 14 years ago when he started developing it. But what he said was like, I'm going to try on my own to develop a programming language. So I have to make some very distinct choices if there's any chance of success, given that the chance of success for a programming language is extremely low. And one of the big things he did is embrace an existing platform, Java. Right? So this is something that people continue to complain about, even though the fact is we run surveys and we get tons of people from Java because people like the Java ecosystem. They don't necessarily like Java the language, but they like the ecosystem. They can use Clojure in a very targeted way and get the benefits without sort of having to relearn everything else. And the other smart thing about doing it this way was, Rich said, oh, I'm going to do Lisp. And people think, oh, Lisp, that's so crazy. But the thing that makes sense about Lisp is raise your hand if you've ever done a Lisp interpreter. Right, so that's like 5% of the audience or maybe 3%. But still, that's a surprising number. And most people that have done it realize, you can do it in 5 days. You can write a Lisp interpreter. It's not hard. So Rich picked Lisp not because, oh, that's cool. I mean, that is cool. But it's possible for one developer or a small team to maintain that, right? It doesn't require a lot of people because Lisp itself is a fundamentally simple thing. The other thing about picking Java is that you get an optimizing compiler for free. So You don't have to spend time, figuring out how to inline and methods, polymorphic inlining, all this stuff, or a concurrent GC. These are all solved problems, right? These are the types of things that people that want to do native languages, you end up spending, decades making that stuff work well, as has been shown by things like the JVM, or even things like Haskell, right? Like you look at Haskell, and that's like 30 years of effort to get something that performs well. So Rich picks an existing platform that he knows is popular. That's a very specific trade-off, right? That you've limited yourself to what the JVM can do, but you get the benefits. And so what he said, well, what can I offer the mainstream, what can I offer that they are not familiar with? And so Clojure embraces functional programming as the way towards building simpler software. A lot of people get the history wrong here. Rich Hickey actually invented the persistent data structures that are extremely popular now, both now in imperative languages as well as in functional programming languages. He took a theoretical text, which was purely functional data structures by Okazaki, which was just talking big O notation about performance, and not talking about what does it mean when you actually run this on modern hardware. Phil Bagwell wrote a paper called Ideal Hash Trees, which was a paper on a mutable data structure. So Rich took theoretical work plus a research paper, and then he implemented a immutable variant based on those two things, and then proved on the JVM you got better than the predicted performance because of the nature of modern hardware and optimizations by the JVM. So the hash array map tree and the bitmap vector tree, those were actually Rich Hickey innovations that later, of course, appeared in Scala, Haskell, wherever else they appeared. There's implementation in C++, JavaScript, so on and so forth. So Clojure was basically an experiment to see, okay, what happens if we make a programming language for the JVM which has better state management than the JVM itself? If you've ever seen this book by Brian Getz, Java Concurrency in Practice, Clojure is pretty much a riff on all the scary things that can happen in multi-threaded programming. The scariest things, let's make sure that those things are not things that programmers will encounter. And that's supported by, again, with these persistent data structures, and then adding really a handful of concurrency primitives that are just slightly higher level than what the JVM provides. And 10 years later, people like it. I mean, people, Oracle's using it. There's people on Amazon using it. Apple's saying they're hiring Clojure programmers. So it works for a lot of programmers working in the mainstream because, again, they're already on the JVM, and they just want to pick a more agile programming language for their process. And this is reflected, right? These design choices are reflected when we do the surveys. More than 30% of our developers are Java programmers, right? And then you add JavaScript, it's 50% of our developers are Java and JavaScript programmers. People look at Clojure and think, oh, it's got to be like Haskell programmers and Scheme programmers and Common Lisp programmers. And these are the top 8 demographics from where programmers are coming from. Those things are not even on this list. For many programmers, Clojure is the first time they've ever used a Lisp. It's the first time they've ever done any form of sort of disciplined functional programming. So hopefully that gives you a sense of the design trade-offs that were made in ClojureScript. And now I want to talk about specifically Clojure. Now I want to talk about ClojureScript. A lot of the ideas transfer, but then there were some unique decisions that were made in ClojureScript that sort of affected its history, and that's really the meat of this talk. ClojureScript was announced in 2011, so it's 7 years old. It's not new, and there's still a lot of stuff that we're working on, but I want to talk about the beginning to sort of give some context. At the time when it was released, I was working in the New York Times. I was working with Jeremy Ashkenazi, who created CoffeeScript. So CoffeeScript sort of showed the world that actually maybe compiling the JavaScript could be practical. Fast forward to 2008, believing this wasn't going to be the case sounds ridiculous because everybody compiles to JavaScript, even if you're writing JavaScript. But in 2011, it seemed wild to compile Lisp to JavaScript. And then really the only other thing that was really happening that people were adopting with any sort of large amounts was CoffeeScript. So CoffeeScript did a thing which we did not do, right? So this is like the trade-off balance thing. CoffeeScript in 2011 said, let's produce readable JavaScript, right? So it was kind of the type of thing that we don't like to do in the Clojure community, which is to make a sort of a short-sighted decision. So CoffeeScript produced readable JavaScript 2 years later, every major browser had source mapping. This was something we were like, not going to do this because source mapping is probably going to happen. Do not care about producing readable JavaScript. But we actually had a more important motive for not producing readable JavaScript. We wanted to produce JavaScript that was targeting the Google Closure compiler. So this is another sort of, I would say, Rich-Hickian move, which is that instead of saying, okay, we're going to build all this stuff ourselves, which it's impractical, there's not enough of us to go around to make that happen, what work has already been done, and can we simply add to ourselves on top of an existing sort of platform that gives us a ton of value? So something that people weren't aware of was Google Closure Compiler. This is almost unused in the JavaScript community, and certainly outside of the JavaScript community, outside of Google, and even the wider program community, people didn't know about this. So Google produces all of its JS properties with this, right? Google Docs, Gmail, all of their JavaScript goes through Google Closure Compiler. And that's closure with a S, not with a J. So what does this do? What did it do? And it still does to this day things that JavaScript tools don't do. It does something that was very familiar to JavaScript programmers, minification. But it does tree shaking, which still to this day is not done effectively in the JavaScript world because people do not program with conventions that allow for aggressive tree shaking. This has changed with something called rollup, where people are now producing libraries that are amenable, but still it's not as precise as Google Closure, because Google Closure can look at your function, say there's no side effects, and remove individual functions from your library. So I can load a library that has 10,000 lines of JavaScript. If I use one function, I'm only going to get that one function. All the other code will get eliminated. It also does an advanced thing which does not exist in JavaScript still, and this is cross-module code motion. So the whole point of doing all this work is that you're targeting a browser, you care about time to load, time to see the screen, time to see the app, time to get functional, right? Latency. So decreasing the payload is extremely important. Another strategy for doing this, which is popular, is splitting up your code to reasonable chunks that can be loaded on demand. That's code splitting. So Google Closure can actually do code splitting, but it can do yet another thing, which it can analyze a function or method, even an individual method on an object in a higher level module, and say that method is only needed in this leaf module. And it will push individual methods all the way down to the location where they're actually needed. And again, this is still state of the art, even though Google had this working back in 2011. And it also presents a large standard library. It's 1/3 of a million lines of code that's been tested against browsers back to IE6. So this was a very strange choice, and even in the Closure community, people were scratching their heads. Why Google Closure? And I think now it's become clear that it was the right thing to do. And in fact, in this respect, ClojureScript is surprisingly still state of the art through Google Closure. One funny thing is that Rich came out with this, and that was very interesting because that took a while for the community to understand these sorts of trade-offs. Was that ClojureScript actually shipped without persistent data structures. It was copy on write. And what happened was that I came on board in 2011 and 2012 with another open source developer. I said, let's see if ClojureScript's persistent data structures can be implemented in JavaScript, and what's the performance characteristic. At the time in 2011, Google had announced V8 in 2009, and my hunch was this, is that Lars Bach worked on Hotspot, and it's really the Hotspot and all the optimizations that allowed persistent data structures to work so well in the JVM. Now they're working on JavaScript. I suspect that we'll be able to get basically within an order of magnitude of JVM performance. It turns out now, when I say within order of magnitude, on modern JavaScript engines, it's only 1.5x slower than the JVM, the performance of persistent data structures in JavaScript. But anyways, on V8, we did a prototype in pure JavaScript, and we saw good performance, much better than copy on write. And then I knew that V8 was going to kick off an arms race between SpiderMonkey and JavaScript Core, and I said, if we do this now in 2012, by the time 2013, 2014 rolls around, it will be the same performance on every major JavaScript engine. And that actually turned out to be true. And actually, V8 is not the fastest anymore. JavaScript Core actually runs laps around V8 now with respect to ClojureScript performance. ClojureScript on JavaScript Core for serial performance is nearly as fast as the JVM. And so this is exciting stuff, right? So here we made another decision, which is what's not what the best choice is right now. What's the best choice knowing where technology is going, right? Where is it going to go? Where are the other engines going? Let's do that. And by the time, we have to be patient, but when we get there, we'll be able to reap the benefits. And this happened in a big way, which we'll talk about in a second. But I started going to JavaScript conferences in 2012 to 2014 and trying to convince people to use this. And still, in some sense, the mainstream wasn't ready for this. Functional programming still wasn't big. This talk, specifically, React wasn't yet huge. So there were still challenges to make people understand that ClojureScript was offering something that was new and perhaps better than what was happening in the JavaScript world. But still, convincing people is hard. Like programming languages, in the end, is a huge marketing problem. So after doing a bunch of talks, you didn't see that many people coming from JavaScript. We run surveys, and JavaScript was always behind Python and Ruby. Python and Ruby were always more people coming to Clojure than JavaScript. And so it felt like, we're doing this client-side thing, but very few people are coming. And it felt like, is ClojureScript just for alpha geeks? Are we a little bit too ahead of the curve? That's how it felt. At the same time, going back to the analogy of Go, we'd really made some good technical decisions early on. And a funny thing happened, which is that we made all these decisions, and then the moment came, and we took it. This is the one game that Isidore won against AlphaGo. Lee Isidore played this game fully in his style. He made it the most complicated situation as possible. That's how he plays. And then he found something. AlphaGo predicted there was a 1 in 10,000 chance a human would play it, didn't analyze it correctly, and then collapses, and Isidore wins this game. The point here is, if there's an opportunity, you should take it. In our case, that opportunity was the appearance of React. So React showed up in 2013, summer of 2013, to basically much ridicule, because it was announced at JSConf, and people said, that's a joke. You're writing JavaScript with XML literals. This is stupid. Nobody's ever used it. My friend Brandon Bloom says, you should actually look at it again, because it's actually a functional thing. It allows you to do functional UIs. And I said, really? So Pete Hunt, who was at the time evangelizing it, was in New York. Me and Brandon Bloom, we went and had lunch across the street from the New York Times. And over the course of an hour, I determined that, yes, we could hook up persistent data structures to React, and maybe the result will be interesting. I spent about a week over a Christmas break, and I made a prototype called Ohm, and I demonstrated with a compiled to JavaScript language with persistent data structures, which are provably slower than mutable data structures, I was able to write a naive, simple JavaScript program that was 4 times faster than the naive Backbone program, right? Backbone was the big thing back then. So 4 times faster than Backbone, naive. And I was still 2 times faster than React with JavaScript data structures, naive, right? So what would have appeared to anybody to be all the wrong ideas, I outperformed all standard methodology around doing UI work. I showed that functional can be faster. This is the most popular blog post I ever wrote. I think it had 135,000 reads. It was the top of Hacker News. And in fact, the React team says this was the moment where people came back and looked at React a second time. And for us, it was huge. Overnight, basically, people in Clojure immediately started building React UIs with ClojureScript. And then a lot of things sort of snowballing. Because, again, we had made a lot of interesting decisions. And this was the key moment. Bruce Hammond did this thing called Fig Wheel, where he realized we already program functionally. React gives us functional programming. I wrote a blog post that demonstrated you could do trivial time travel with React and persistent data structures. And he said, oh, we can do live coding of UIs, like Smalltalk did, or the way you do in Common Lisp. And so he built this thing called Fig Wheel, which hot loads your code. And the reason people love ClojureScript is that you can fire up Fig Wheel. You can be 7 steps into some UI flow. You can change any component you want, and you'll never lose the state of your application. So when you watch a JavaScript person do something, they change something, they refresh, and they have to click through 7 steps to get back to the state they were in to do it. And that's something you can avoid in a purely functional architecture, because the state and how the components work are cleanly separated. The other lesson here is that in a small team, we really have to focus on the essentials, and we have to trust and encourage people to find opportunities to innovate outside of core development, right? It's just one person at Cognitech doing development, right? So I really need the community to try stuff. And this worked out really great. I just want to show this before I move on. So here I have Figwheel. I'm not going to show too much live coding here, but the point is this is nothing that we worked on. We just enabled it by providing the foundation. So this is a REPL that's connected to the browser. Here I make a mistake, and this is nothing that we do. So he has Elm-style errors where I've made a mistake, I didn't import the library. It tells you exactly what went wrong, it shows you all the errors. I can go ahead and import that. I can load that definition. I can say, give me all the styles. And this is directly connected to the browser, right? I'm just live coding. The way that ClojureScript programmers develop is they start a REPL session and they never stop, right? It's always live programming. This is very different from conceptually how most programmers think of REPLs. People think, oh, I'm in the REPL, I test a couple things. In the Clojure and ClojureScript world, you fire up a REPL and you never turn it off. You're just live coding the entire time, interactively. It's a huge productivity gain. One more thing, and then I'm going to talk a bit about the consequences for us integrating another sort of trade-off that we're thinking about. But before I go there, one thing that was interesting when ClojureScript was announced was people thought, oh, this ClojureScript's cool, but you did this weird thing, Rich, where you are statically ahead of time compiling the code base, so you can't do the Lisp tricks. You lost eval. So when we started targeting Google Clojure, we lost eval. And the thing is, this is a typical case, again, where you have to be patient. Let's wait until the moment we can recover this thing that people need. The reason we didn't do it at the beginning was because JavaScript programmers, they basically aren't going to look at your thing if your baseline payload is more than jQuery. Baseline payload for jQuery back in 2011 was 32K, right? For us to have the capability to eval in the target meant that we would be at a 300K payload at minimum. Right, at minimum, which would automatically throw you out of the running. And in fact, there were many compiled to JavaScript languages that did this, and they were fun for very specific projects or as toys, but you couldn't get a community to adopt it because, again, it was too far away from what's considered best practice, that you want to minimize the payload. But July 2015, 3 years ago, Clojure added the one feature that we needed to allow this to be optional. So I went ahead and tweaked it so that ClojureScript can compile itself. So ClojureScript can compile itself into JavaScript. And I made a very specific decision here, which I said, we don't know what people want to do, and we don't know what's going to happen with Node and how people want to integrate with Node. We don't know if you want it in the browser, you want it on Android, you want it on iOS. We don't know. So we provided the most minimal thing that makes no decisions, that says nothing about I/O, that gives you the ability, the framework to do eval wherever you would like. And it turns out that meant there was more work for the community to solve, but in the end it was the right choice because now everybody's free to do it how they like. It allows things like, right now you can go to the Apple Store and you can download Replete. It's an iOS application that runs bootstrapped ClojureScript. So all the things that I'm showing about being in the REPL, it can be right there in iOS. People have done, there's a thing called Plank, which is bootstrapped ClojureScript on JavaScript core. So you can write ClojureScript code that interops with C, because JavaScript core interops with C. It must. It integrates with WebKit. So there's a lot of possibilities now, again, because we were patient and said, let's just let people see the value of doing it this way. So the last thing I want to talk about is, so fast forward to 2018, and what are the things that we're struggling with now? What are the sort of the things we're sort of trying to figure out what's the right way to go about this? What's the right balance? What's the right trade-off? And now it's really a node module. So I'm sure everybody here now has to do React or some form of JavaScript thing if you're doing anything on the web. But this is, of course, not something you could have predicted, right? Back in 2011, people were like, oh, I'm just going to write bash scripts to concatenate my scripts. Some people were using Bower. There was just a million different ways to build your front end. At the New York Times, I worked on a project where people literally were building this big project, and it was like 3,000 lines of an Ant file, an Ant build script. They're using Ant to generate the final JavaScript payload. It was crazy. It sucked. But what happened was that NPM has more or less won. People put all of their front-end libraries into Node, and they build their stuff. The issue with this, that if those of you that have done it and were there early on, is that there were no standards about how to put modules and how to organize modules in Node. And in fact, a lot of the tools have all these edge cases to work around the fact that there's not enough convention. And so what's happened recently is that we are now, finally, 7 years into ClojureScript's life, there's finally an influx of JavaScript developers. And I'm surprised, but I shouldn't be, because what's happened is that people who are doing JavaScript for long enough are like, well, JavaScript's cool, but it's getting really complicated now. It's actually a lot of work, right? In some sense, there was this narrative, oh, JavaScript, it's simpler than Java, but I would actually argue modern JavaScript development and modern Java, it's about the same. It's friggin' complicated. And so we're seeing an influx from the JavaScript world because people are at the point where they're willing to try something else. They're willing to see if something's better. But one issue is that they're coming to ClojureScript with an expectation. Oh, I can just use Node modules. And we are slowly trying to figure out what to do about this. And one thing that we want to do, we want to show the world is what happens if you could advance compile Node modules. Meaning that I could take any Node module and I could apply dead code elimination and advanced code splitting on any random thing I find in Node. So that's an alternative we want to demonstrate. So that's one thing we're working on, so we're not rushed. And the other thing is that truly to get every random module, I don't know if we care about that, but we do care about showing that this can be done with React and Material. And in fact, we've already demonstrated a year ago that we can produce the smallest version of React. It's smaller than anything you would get from JavaScript tooling and things like code splitting, all that stuff. It just works. Non-goals, things again that we don't care about. It's like we really don't care about any random module. We care about the big ones, though of course we'd like to include more over time. And finally, what we've discovered is that not everything is a programming job. Not everything is compiler work. We've discovered that for a surprising number of Node modules, you don't need to do anything. In fact, the best solution is communication. You reach out to the maintainer and tell them, you're doing this one thing in your package.json, which is causing a problem for me. As far as I can tell, it's not important. Let's just stop doing that. And that would immediately make that module usable from ClojureScript. So anyways, and then sustainability. So hopefully you've learned something about the sort of design trade-offs, how we think about keeping the project sustainable, why we made certain decisions, and what value they have. Again, for me, it's about sustainability. The truth is we're probably going to stay a small team. So hopefully you can see a pattern. We're always looking for the biggest impact with the least expenditure of effort. If some company has built a great thing for us to build on top of, we're just going to use it because that solves our problems. Whether that's the JVM, whether that's Google Clojure, whether that's React. Work we don't have to do. Awesome. Something else that we need to improve upon, which I think this talk is sort of part of that, is setting expectations. I think people come to Clojure and ClojureScript from languages that have bigger committees or bigger teams. And we think about the problem differently. We believe that we can distribute responsibility, and innovation doesn't have to happen all with this small core team. And then also I think the thing that we've learned is that you have to have a heavy dose of patience. It really is worth waiting to see what the right way is instead of rushing to any particular decision. Anyways, thank you. And I'll probably have to take questions later. I'm probably running out of time. Thanks.